All of Chapter 8 has been dedicated to studying techniques of integration. In this last section in Chapter 8, Section 8.6, we're going to be kind of pulling all those techniques of integration together and looking at them in the context of improper integrals. Integrals can be improper for one of two reasons. The first reason that an integral can be improper is that it has infinite limits of integration. So its limits of integration, instead of going from 1 to 2 or square root of 3 to 4 or something like that, has an infinite limit of integration involved. So it could be a positive limit, it could be a negative infinite limit, or we could have both negative to positive infinity for limits of integration. So this is one reason why an integral could be considered improper. The second reason an integral could be considered improper is because of a discontinuity. So let's go ahead and consider the integral of 1 over x minus 2 dx. Now if we look at this between 0 and 4, we realize that at x equal 2, this denominator is equal to 0. And when this denominator is equal to 0, the fraction is undefined, so I have a discontinuity here. So for this case, x cannot equal 2, but that's kind of a problem because 2 is in the interval between 0 and 4. I have a discontinuity at 2. And if we remember what integration is usually about, it's finding area underneath curves. And of course, we have to be careful about signed area. 1 over x minus 2 would be an asymptotic line at x equal 2. And then the graph would look like something like this. So I'm talking about finding the area underneath this curve between 0 and 4. And you can see pretty quickly that between 0 and 4, I kind of have a big old mess. So there's 0, 1, 2. Here's 3, 4. So here's my bounded area here and here. But to look at the area between 3 and 4 there is kind of difficult. Or so between 0 and 4 is kind of difficult because I have an asymptote, and then I also have area above and area below, and then I have to be concerned about approaching this asymptotic line from the left and from the right. So two reasons you can have an improper integral. I have an infinite limit of integration, or I might have an improper integral because I have a discontinuity over my limit of integration. And of course it's possible that you could have an improper integral because of both reasons. Let's go ahead and look at an easy example where I have an integral that works out just perfectly. So let's look at the integral between 1 and 2 of 1 over x to the 4th dx. Now the thing that would make this particular integrand improper is if x equals 0. But notice my limits of integration go between 1 and 2. 0 is not in the interval 1 to 2, so I should be fine. This is not an improper integral. But let's go ahead and integrate this. This is a nice little Calc 1 problem. So we flip our exponent up top, we add 1, divide by the sum. When I add 1, I get a negative 3 divided by negative 3. So I get negative 1/3 x cubed, negative 1 over 3x cubed, evaluated from 1 to 2. So the way I work these is I pull the negative 1/3 out, and if I pull out the negative 1/3, I'm left with 1 over 2 cubed minus 1 over 1 cubed. Negative 1/3, this would be 1/8 minus 1, which is going to be a negative 7/8. So I get 7/24 here. So 7/24 is my solution. Now here's the question. Does this involve an area? Is this signed area? Is this above or below the x-axis? So here's the graph of 1 over x to the 4th, just as a general curve sketch. Well, I'm looking from 1 to 2, let's say. So this is my region that I'm trying to find. So this is indeed area of the graph of 1 over x to the 4th from 1 to 2. So it's bounded area. It goes toward a particular value. So we can kind of see what we're going to be up to here. Now I want to take the same identical graph, 1 over x to the 4th, and this time I would like to look at this in terms of an area from 1 to infinity. So same function, but my limits of integration will now go from 1 to infinity of 1 over x to the 4th dx. Now how do we work this? Well, first of all, this is an improper integral because I have an infinite limit of integration. Okay, so I'm going to have to figure out how to do that. Remember, I can't plug infinity in because infinity is not an arithmetic value. I can approach infinity, so you already know that limits will be involved somehow. But let's go ahead and look up at this graph that we already drew. Before I was just interested from 1 to 2, but now I'm interested from 1 to positive infinity. So you might say, well, if I go from 1 to positive infinity, I'm going to be continually adding area. And if I'm continually adding area, the area will continue to get larger and larger and larger. So I can't find that area because it's going to just keep getting larger and larger. Well, let's see if that logic holds with this particular problem. With this problem, what we're going to do is we're going to change this value of infinity to some constant. A lot of times we use a's, b's, or c's. And then I'm going to rewrite this in terms of a limit. So I'm going to look at this as the limit as a approaches infinity of the integral from 1 to a of x to the negative 4th dx. So what I've done is I've replaced infinity, because I can't plug infinity in, with an a. A will approach infinity then using our limit notation. You can't drop the limit notation, you need to keep it along. So now as we integrate x to the negative 4, I've already integrated that from up here, I get negative 1 over 3x cubed. And I need to evaluate that from 1 to a before I can take a limit. So rewriting, I have my limit as a approaches infinity. I'm still going to pull out that negative 1/3, and again that's a preference. That leaves me with 1 over a cubed minus 1 over 1 cubed. Now I have my a. I should be able to take my limit. So as a approaches infinity, what ends up happening is this fraction that the denominator gets larger and larger and larger, which means the overall fraction gets smaller and smaller and smaller. It goes towards 0. So I've taken the limit. This piece went to 0. This piece will just be a negative 1. 1 cubed, of course, is 1. So I get 1/3. Well, what does that mean? Well, it means the area, again, I'm just going to blow up this first quadrant here, between 1 and infinity on my x-axis is 1/3. And it approaches 1/3. It doesn't actually equal 1/3, but it approaches 1/3. Well, how could that be? Because we're continually adding area, you would think that we would get an area that's larger and larger and larger. But what's happening is we're adding an area that's so small that no matter how often I add up those very, very small pieces, it's not getting any larger than 1/3 for my total area. So again, first of all, we say this area is not bounded. It's bounded on the left by 1, but it's not bounded on the right because I have an infinite limit of integration. And we note that the area, this value is getting closer and closer to the x-axis so quickly that it's basically bounding the total area even though the limits are not bounded. And so what we say then, that this area converges to 1/3. And this terminology is going to be important. We say converge or diverge when we're referring to whether I have an area that goes toward a particular value or if I have an infinite limit of integration that diverges. So sometimes this could go toward infinity, and we'll see some problems like that. Let's go ahead and look at a very similar graph. This one, let's look at the integral from 1 to infinity again, but this time instead of 1 over x to the 4th, I want to look at 1 over x dx. We're going to do the same thing. We're going to replace this value with a constant similar to a or b or c, and then we'll look at the limit as a approaches infinity of the integral of 1 to a of 1 over x dx. Well, I can't flip this one up top and work it. I need to remember that the integral of 1 over x dx is the natural log absolute value of x, and of course we need to drag along our limit notation. And this is going to be important. I notice a lot of people were using parentheses here at this point. The integral of 1 over x dx is the natural log of the absolute value. This parenthesis notation does not indicate absolute value, so you need to make sure you have absolute value. And we're going to be evaluating this from 1 to a. Again, dragging along the limit notation, the limit as a approaches infinity. Okay, when we plug in our upper minus my lower, I have natural log absolute value of a minus natural log absolute value of 1. And the natural log of 1 we know is 0, so this leaves me with the limit as a approaches infinity, the natural log absolute value of a. Well, as a approaches infinity, I'm approaching the natural log of infinity, which is infinity. So this is telling me that I have infinite area above the x-axis because we can look at a quick graph here. The graph of 1 over x dx, remember, is in the first and third quadrants, and I'm interested from 1 to infinity. So that's this area right here. And you might say, well, wait a minute, that's very similar to the area that we had up in this direction. But this particular graph is hitting the x-axis a lot faster because I have 1 over x to the fourth. Then the graph of 1 over x is going toward the x-axis. So what we end up saying here is there's an infinite amount of area underneath the curve of 1 over x dx from 1 to infinity. So we say that this diverges. Remember, our last one converged and went toward a particular value. This one's going toward infinity, so we say that it diverges. And that's an important thing to note for each one of these problems. Let's go ahead and look at another example. In this example, we're going to be looking at the integral from 0 to infinity of e to the negative x dx. One of the nice things to be able to do with these types of graphs is to do a quick little curve sketch. E to the negative x is the same as 1 over e to the x, so instead of exponential growth, this is exponential decay. So if you wanted to graph a couple points here, you could plug in 0. E to the 0 is 1, so here's kind of my hinge point, and this is what this graph looks like. So I'm looking at the area underneath this curve between 0 and infinity. Now we've already seen two examples of this unbounded on the right by infinity type of curve, and what we need to determine is, does the graph of e to the negative x go to the x-axis fast enough to make that area approach a constant instead of infinity? So let's go ahead and rewrite this. Again, we'll take our limit as a approaches infinity of the integral from 0 to a of e to the negative x dx. Now these integrals are pretty easy to do compared to some of the ones we've been doing the last couple weeks with partial fractions and trig sub, integration by parts. So here we can just do a nice straightforward u substitution. Here we'd let u equal negative x, du is a negative dx. We'd multiply by a negative on the inside, compensate with a negative on the outside, and I'm left with the limit as a approaches infinity of a negative integral of 0 to a of e to the u du. And actually this brings up a very important point. These limits of integration from 0 to a should not be here right now, so let's remove those. The limits of integration from 0 to a are appropriate here because 0 and a are values of x. But now that I've rewritten my problems in terms of u, 0 and a are no longer appropriate. I would have to convert those values. So let's go ahead and leave this without limits of integration. You could convert them, but I'm just going to leave them as is. If you, in a trig sub problem and convert everything to thetas or convert everything to u's, you need to drop your limits of integration. So here I'm left with the limit as a approaches infinity, and I don't really even have an a yet, of the integral of negative integral e to the u, which is negative e to the u. U in this case is a negative x. Now I can evaluate from 0 to a. Limit as a approaches infinity. I'm going to factor my negative out front, and I'm left with e to the negative a minus e to the negative 0. Limit as a approaches infinity. I have a negative sign out front. E to the negative a is 1 over e to the a minus e to the 0 is 1. Now as a approaches infinity, e to the a approaches infinity, 1 over a very large number approaching infinity is actually going towards 0. So what I'm left with here then is minus a negative 1, which is 1. So a very complicated way of writing the number 1. So the area underneath the curve of e to the negative x from 0 to infinity approaches 1. So we say that this area converges, or this value converges toward 1. Now we've looked at quite a few examples where we have improper integrals because of infinite limits of integration, but let's go ahead and look at some integrals where we have an improper integral because of a discontinuity. First one, pretty easy one, let's look at the integral from 0 to 1 of 1 over the cubic root of x dx. And again, a nice little curve sketch is a handy thing to know about here. Well, the integral of 1 over x we've graphed before, first and third quadrant, and actually this is the general shape of the graph of 1 over the cubic root of x as well. Of course, it's going to have a different scale to it, but it's the same general shape. Now we're interested in this curve between 0 and 1, so here's between 0 and 1. So it looks like it's an infinite amount of area because this graph never hits 0, so they're going to keep adding area. But the question is, does it go toward the y-axis fast enough to make that area bounded or go toward a particular value? So we're going to use the same approach here. I'm going to kind of look at this and think, okay, this makes this an improper integral. I have a discontinuity here. Now if we think about the graph between 0 and 1, here's 0 and here's 1. And we can see that it's going to kind of do something, actually not quite that. It's going to run into this point. It's going to be more like this. Between 0 and 1, I need to take a limit, and it has to have something to do with 0, but I can't approach 0 from the left. That wouldn't make sense because I'm interested in this area right here. So I need to look at this in terms of a limit approaching 0 from this right direction. Left-hand side would be from the left, right-hand side would be from the right, so I would be approaching 0 from the right. So let's go ahead and rewrite this one. This will look like the limit as a approaches 0 from the right of the integral from a to 1 of 1 over the cubic root of x, which is the same as x to the negative 1/3 dx. That's how I would rewrite this. Dragging along the limit notation, the limit as a approaches 0 from the right. When I add 1 to a negative 1/3, I get a positive 2/3. When I divide by 2/3, it's the same as multiplying by 3/2. And then of course this is evaluated from a to 1. I always pull all the constants out that I can. Whoops, whoa, what happened there? Let's see if we can get some of this back. Okay, we got it back. So, whoa, there it went again. Okay, hopefully if we're very careful here, my problem won't disappear. So we had a 3/2 here, and this was evaluated from a to 1. So this is equal to the limit as a approaches 0 from the right of 3/2. And again, I always pull out my constants. 1 to the 2/3 minus a to the 2/3. 1 to the 2/3, of course, is 1. So I'm left with the limit as a approaches 0 from the right, 3/2 out front, 1 minus a to the 2/3. Well, we can plug 0 directly in now, and if we plug 0 directly in, you want to think about it as approaching from the right, you can, but this piece goes towards 0, which leaves me with 3/2 times 1, which is 3/2. So that area converges to 3/2. So this is convergent. Now, not all areas converge. It seems like quite a few of ours have. Let's go ahead and look at another example where that might not be the case. Let's look at the integral from 0 to 2 of 1 over x cubed dx. Now, there's a relationship here, 1 over cubic root of x, 1 over x cubed. So you might think, okay, this looks like to me that it will probably have the same type of behavior. Well, let's look up here. On this one, we are going between 0 and 1 of 1 over the cubic root of x. Here we're going 0 to 2 of 1 over x cubed. Now the graph of 1 over x cubed will be in the first and third quadrants, and 0 to 2 might look something like this. So again, we're trying to find this area. We're trying to figure out if this is bounded area, if this graph goes toward the y-axis fast enough to bound this area. First thing we do is rewrite. We take the limit as a approaches 0. We're going to be from the right because we're between 0 and 2 of the integral from a to 2 of x to the negative 3 dx. Nice little Calc 1 problem. Drag along my limit notation. X to the negative 3, I'd add 1 to give me a negative 2, divide by the sum. Rewriting with our limit notation, I'm left with negative 1 over 2x squared. And this is going to be evaluated from a to 2. So I'm going to go ahead and factor out a negative 1/2, and I'm left with 1 over x squared, which would be 1 over 2 squared minus 1 over a squared when I evaluate with my limits of integration. So limit as a approaches 0 from the right, negative 1/2 out front. Here I'm left with 1/4. Now, this one's a little bit tricky. If you plug 0 into this piece right here, you get something that's undefined. Okay, so does that mean I'm approaching infinity or negative infinity? I'm undefined, I know that for sure, and I'm only approaching from one direction, so let's see what's happening here. Now, I'm looking at 1 over a squared. If you want to look at negative 1 over a squared, you can, but I want to just look at 1 over a squared. 1 over a squared has a general shape in the first and second quadrants, and I'm approaching 0 from the right, so this graph is approaching positive infinity. So this is going to look like minus infinity. So I have negative 1/2. 1/4 minus infinity is a negative infinity. Minus a negative is the same as a positive. So when we look at this here, when I come up with my value of positive infinity, I can say that this area diverges. It's getting larger and larger and larger, and it does not go towards 0. So far, all of the integrals that we've looked at have been pretty straightforward, some nice, Calc 1 or nice easy use substitution type problems. But what you need to remember for improper integrals is all of the techniques of integration can show up for an improper integral. So if all the techniques can show up, that means we could have something as easy as a use substitution, or maybe something that doesn't even need a use substitution, like the sine of x, the integral of sine of x would be a negative cosine of x. We could have a use substitution, we could have a integration by parts, we could have a partial fraction, we could have a use substitution, or sorry, a trig substitution. What else did we have? We also had trig integrals, where we had sines and cosines to high powers. So all of these things can still show up, but now what we've added is this complexity of an improper integral. And remember, an improper integral can show up for one of two reasons. I could have an infinite limit of integration, or I could have an integrand that had a discontinuity across the limits of integration. So let's go ahead and look at some more complex problems. Let's look at the integral from negative infinity to 0 of x e to the negative 2x dx. Okay, well this one doesn't look too bad as long as you remember that this looks like it fits the form of an algebraic component and a transcendental. Algebraic times a transcendental we can usually integrate with integration by parts. If you let u equal negative 2x, du is a negative 2, and I'm left over with this value of x, so that kind of gives me my indication that integration by parts will work nicely here. You could use the tabular method with this as well. I'm going to just go ahead and straightforward use integration by parts here because I only have to worry about one iteration. So for integration by parts, you choose a u and a dv. U in this case will be my algebraic component. That leaves e to the negative 2x dx for my dv. Remember, you take derivative down. The derivative of u would be the derivative of x, which is 1 dx. And then you integrate up. The integral of e to the negative 2x dx, so this is the integral of e to the negative 2x dx, is we're going to let u equal negative 2, du is, negative 2x, du is a negative 2 dx. So I multiply by 2 on the inside, compensate with a negative 1/2 on the outside, and I'm left with negative 1/2 integral e to the u, which is negative 1/2 integral of e to the u, which was negative 2x. So you have to review those if you don't remember them, because now we're kind of using them like they're really easy to figure out. So rewriting this, what ends up happening is I have the limit as a approaches negative infinity of the integral from a to 0 of x e to the negative 2x dx is equal to the limit as a approaches negative infinity of, and of course we need to evaluate these, uv, which is going to be negative 1/2 x e to the negative 2x, minus the integral of v du. And my limits of integration here go from a to 0. Now this is the piece I need to integrate next, so dragging everything along. Limit as a approaches negative infinity of negative 1/2 x e to the negative 2x. Now here, this is going to be kind of interesting. I'm doing the same exact integral as I just did up here. So I'm looking at e to the negative 2x dx. with this 1/2 pulled out front. So this 1/2 is pulled out front, and I'm left with the integral of the e to the negative 2x, which is going to be negative 1/2 e to the negative 2x. And that's easy to find from exactly what we did right up here. Now this is evaluated from a to 0. So we need to do quite a bit of simplification here before we can effectively take that limit. So this is equal to the limit as a approaches negative infinity, negative 1/2 x e to the negative 2x. Now minus a negative, or sorry, positive times a negative is a negative 1/4. But this e to the negative 2x I'm going to flip. E to the negative 2x in the numerator becomes e to the positive 2x in the denominator, and this is evaluated from a to 0. So let's look here. The limit as a approaches negative infinity. Now we have to go ahead and plug in our upper minus our lower. So our upper, we plug 0 in first, and when we plug 0 in here, we get a 0 back out. However, when we plug a 0 in here, we get 4 times e to the 0. E to the 0 is 1. 1 times 4 is 4. So I have a negative 1/4. That's my upper. Minus my lower. So plugging in my lower, I have a negative 1/2 a e to the negative 2a minus, and I think we'll flip that too, but we won't flip it right now, 1 over 4e to the 2a. And now I should be able to either be ready to take my limit or simplify it more. Now because I have an a approaching negative infinity, I actually think I'm going to flip this piece back up instead. And the reason being is I'll have a negative times a negative, which will give me a positive exponent. If I plugged a negative infinity, or I approached negative infinity down here, I'd end up flipping it up top anyway. So it's just kind of to save an extra step. 0 minus 1/4 is a negative 1/4. The limit of a constant, of course, is just a constant, so we'll be looking at that in a second here. Minus a negative is the same as a positive 1/2 a e to the negative 2a, minus a negative is the same as a positive 1/4 e to the negative 2a. And again, I chose to flip that up top because my limit is a is approaching negative infinity. So when we look at evaluating this, the limit of this constant of a negative 1/4 is a negative 1/4, and let's just go ahead and plug in or approach negative infinity. This piece right here will be 1/2 times a negative infinity, which is a negative infinity. E to the negative infinity times the negative 2 is e to the positive infinity, which is a positive value. And then here for this piece, I'm going to be left with e to the negative 2 times negative infinity. E to the infinity is infinity, so I'll be left with an infinity here. And the question is what is this? So it looks like I have infinity here minus some other degree of infinity here. So this looks like infinity minus infinity, which is indeterminate, if you recall back from when we learned about L'Hopital's rule. Now it's not indeterminate L'Hopital's, it means we need to rewrite and do a little more work here. So let's go ahead and leave this negative 1/4 out front and try and rewrite and work with this a little bit. So we're left with the limit, I'll say a plus here, the limit as a approaches negative infinity. What could we do here? Well, at least looks like we could find a common denominator. So I'm going to find a common denominator up here by multiplying top and bottom by 2. And it looks like I could pull out a 1/4 e to the negative 2a. And if I pull out a 1/4 e to the negative 2a, I'll be left with 2a plus 1. Okay, so does this make this a little any easier to just determine what's exactly going on here? Well, we could actually look at this one of a couple ways. We are actually ready to take this limit right now. This piece right here would go toward positive infinity because I have a negative 2 times a negative infinity. So e to the positive infinity is infinity times a 4th is in positive infinity. This piece right here is negative infinity. So I multiply these together, have a positive times a negative. So this would look like negative 1/4 minus infinity is minus infinity. So this area actually diverges. So this is divergent area. Now, the improper piece, we really didn't do a lot with that. Most of this was focusing on our integration techniques of integration by parts. So again, all of our old integration techniques can work here. The tabular method, the recursive method, partial fractions, trig sub, they all will work with improper integrals. And they can get pretty complicated, but the important part to remember here is do not drop your limits of integration. Keep track of the fact that you're using limit notation as well, and just stick with them because they can get very long. Good luck!